Hello guys, can you hear me well? Can we start? Okay, great. So welcome to Do Things Blazingly Fast with WebAssembly. A little bit about me. I'm Sendil Kumar. You can reach me on Twitter at this tag. I'm basically from India, the southern part of India, Tamil Nadu, and currently I'm living in Netherlands. I'm working at a company called Zebia Labs, where we do DevOps related product. So that's it. So I'm a full stack developer, a big open source lover. I love to do a lot of things in open source. I contribute to many open source projects. I'm part of Rust and WebAssembly working group, where we decide the future of Rust and WebAssembly that works together. And also a team member at Webpack and JHipster. And I love coffee, as do many developers. Yep. So how many of you guys are JavaScript developers here? Okay. Oh, many people. Great. And actually, JavaScript is everywhere. So you can find JavaScript on your React Native application, that is your mobile application. You can find JavaScript on IoT devices. You can find JavaScript on the server side, on the front end, and all the places JavaScript is omnipresent there. The reason why developers love JavaScript, because it's fast. Do you guys agree to it? Okay. It's easy to learn because you can get started easily. Well, yes, it's easy, but let's test it out, the easiness of JavaScript. I have a question for you. What do you think this one will evaluate? It's a true? How many say it's a true? Nobody? Okay. False? Nobody? Come on, guys. Answer one. False? True? Okay. Yes, you guys are correct. The answer is false. Reason? They are objects. The references are different. That makes them false. Great. One more question. What do you think the answer will be here? True? How many say true? Okay. 3. False? Okay. And the answer is true. Why? So basically, when a JavaScript sees a bank symbol before an object, it type checks it, and then it says, okay, this guy is a false. It's a false. And you obviously have an empty array there, which when JavaScript engine is type checking it, it converts that empty array into a string. And when this empty array is again type checked, because you're checking with 0, which means JavaScript considers this empty array as an integer. So when it tries to convert that string to an integer, which is an empty, it converts to 0, which means 0 equal to 0, which is true. So the answer is true. The last one, I promise you guys. What do you think the answer will be here? Okay, the options are this one. How many say this? Nobody? This? How many say that? The right one? Okay, we have somebody saying the right one, but the answer is banana. Anybody can tell me why? Yeah, exactly. So it evaluates to banana. Okay, great, right? Well, this is not a JavaScript 8 talk. I love JavaScript, and I do think we all love JavaScript because it's much more easier for us to get started and learning stuff. But there are some weird parts in the language. Like the language that was designed over in a week, there are some weird parts over there, and it's continuously carried forward, and there are things that you have to know in order to make sure that end-to-end application is working perfectly. And every language has some weird parts. We have to agree that. And there is an amazing talk by this. You can go to this website and see that amazing talk. It's just a 15-minute talk where he is like talking about Ruby, JavaScript, and things that we have the weird parts in those languages. And this is a hello world in Brainfuck. So weird language, of course. So let's see. Just before we dive deeper into this talk, we just need to know how a JavaScript works inside your browser. And how many of you know that stuff here? Okay. Nobody? Okay. Let's see. So what happens when a browser first sees JavaScript? It just goes to that endpoint and fetches a JavaScript code, which is nothing but a string. And this string comes into the picture, and then your JavaScript engine kicks up. For the very first thing what your JavaScript engine does is it parses the entire string, and then it converts them into an AST. AST subtract syntax tree. So once it is done, JavaScript is an interpreted as well as compiled language, which means once the entire string is fetched, It's parsed. It's ready to go and run. But again, there is a compiler built in JavaScript engine which actually converts this in AST into bytecode. And finally, it executes it. But what happens when a function is getting called many times? You cannot go through the same loop of converting, compiling again and again, because it takes time, and time is valuable in terms of browsing or web applications. So the performance is getting lower. So many times when a function is called, there is a guy called profiler, and different JavaScript engines call them in a different way. But the main function of the profiler is to optimize the code. So it just sees, okay, this guy is getting called many times, so let me go ahead and optimize it. I spent some nanoseconds for optimizing the code. At the end, my overall performance is higher. Perfect, that happens. But what if the same function is getting called? You have a for loop that runs for 1 million times. Then what happens? Like, JavaScript marks that function as really a hot function, and this hot function will be sent to another optimizer, which is called as re-optimization step in the JavaScript engine, or plain old optimizer. And this optimizer is responsible for doing more optimizations in the code and then making the performance even more better. But you're spending some time in order to make this re-optimization. What happens in a re-optimization stage is like, it takes some assumption. Like, for example, you're iterating through a for loop. JavaScript engine consider, okay, whatever is going to happen here, it's going to happen only on the integers. Like, everything here is just ints. I'm going to consider this as an assumption. But whenever this loop is break, whenever you introduce JavaScript's dynamically typed language, you can do a for loop over I, and then you can, in the mid of the for loop, you can say like I is equal to a string, hello world or something. You can do that. When this happens, the entire optimization and the re-optimization steps which the engine has taken will be completely lost, and it goes back to the interpretation stage. And then it happens all over again, which is why people are enforcing on monomorphization or using a type system in their application. And finally, when everything happens, everything is garbage collected under the hood. So this is what is happening in JavaScript. Why speed and performance matters here? Anybody? Okay, great. So JavaScript is something that the browsers, that's something you have it everywhere, and you have it on your mobiles too. Mobiles, they are lightweight, and the performance is not comparable to the laptops or the desktops that you have, but it is growing, admit that, but of course, currently it's not that much speed, and you have this high-end devices which kind of work similar, and then you have this low-end devices where you cannot load a single web page much more faster, which means performance matters for you. And of course, you can have gamings. So when you do gamings on a web browser, which means you don't need to worry about the underlying operating system or else underlying stuffs, you just have to make sure that it runs on the browser, which means it can run everywhere, things like that. And of course, more and more people are moving towards IDE in the web, because it's much more safer, cleaner, and you can do whatever you want inside one single browser, and you just need that application. So these are the things where performance really matters. And also in your code, sometimes you need performance, like you need to go for a loop or something, then you need to increase your performance. And there is an amazing thing here, like out of all the things that happens in a web, JavaScript is the most expensive part of the web. It's not images. You can load a lot of images in the system, in the browser. You can optimize those things manually, but in terms of overall web, JavaScript is the most expensive part, and most of the times, your application spend time in executing JavaScript-related stuff. Why? Because once the JavaScript entire string is downloaded, it has to parse it. So this parsing should happen only when you have the entire JavaScript in your picture. It cannot happen when you have only half JavaScript or 50% of the file, which means you have to wait till it gets downloaded, and also it has to parse and start doing that stuff, which is time consuming. And JavaScript is web CO2. This is cool, right? You cannot live without CO2, but of course, more CO2, you will end up in global warming and all those stuff. How many of you have experience seeing this? Or doing this? Okay, we have 1, 2, great. So yeah, so this is something where if you want to drill down to get higher level performance, if you want to get more performance out of your JavaScript, these are some mechanisms in which you can go ahead and find out which function is getting called more number of time, where your lagging is happening, where are the things happening, and then you can go ahead and utilize this graph in order to find out how to make sure your performance is faster. But once you've done this in a Chrome, and then you come back and see there will be a lot of applications, a lot of browsers out there, and in every browser, the parser or the JavaScript engine is different, which makes which insists that you have to understand the internals of the JavaScript engine, which is not quite easy to understand. And you have these weird scenarios where we tested like an array equal to array. We always expect that to be true, but it's not true. And that's basically it. So you have to understand the internals of the engine, which means you have to write some geeky JavaScript there. It's not so easy anymore. You have to understand the performance implications that you're writing, the code, and that causes a lot of problem. This reduces the maintainability of the code. So this completely reduces the maintainability of the code. And we end up in doing this. Why this thing is not loading faster? Or how many of you experience this thing? How many of you are still working on IE6? Nobody, right? Okay. You're all in a good land then. Yeah. So we are experiencing this stuff. And there are various solutions that were tried in order to solve this kind of thing, in order to increase the performance in the web. The obvious first thing is Flash, and somebody killed it completely. And then there were applets, which Java community came forward, and that is also not anymore because you have to wait till the entire jar is getting downloaded into your browser, and then it converts into bytecode, and then it performs something there, which is also not so user-oriented. And then we have Pinnacle. Anybody used Pinnacle here? Okay, it's a native client written by Google. So in the Chrome, you can use Pinnacle in order to run your native code in the browser, but it's also a failure. And finally, we had ASM.js, which is backed by Mozilla. It's like ASM, it's like JavaScript or superset of JavaScript, you can say, which is kind of typed, but it had its own problems because you have to download this entire chunk, and you cannot do the streaming compilation, and which causes its own problem. So there were like a lot of things happening, but if you take a look at these 4 steps, like all these 4 backed by different companies, and those vendors, they are too much focused on their vendors or focusing their product to come up, which made everything to fall apart. But web is awesome, right? Anybody disagree with that? Web is open, and it's evolving. It evolves over the time. You can see like a lot of things are getting added newly into the web. Why? Because it's open, because anybody can go and interact with the community and build something that they want, which is really good. So introducing you guys, the WebAssembly. How many of you here have used WebAssembly? Okay, few. Heard WebAssembly? Okay, many, great. Awesome. So what is WebAssembly? WebAssembly, just before we go there, WebAssembly is an answer to those 4 things that we have. We have experience in building those 4 things. And out of those experiences, we collected everything. And then we said, OK, we are going to create something open such that everybody can use that stuff. And it's not depending on any vendors. It's like an open platform. So we're creating something like WebAssembly. And WebAssembly is nothing like a binary instruction set. That's it on a plane. And it's very fast. As I said, it's built for the open web, and it's debuggable. You can debug WebAssembly. And it's safe because it's running on the same sandbox as your JavaScript, which makes it really safe. You don't need to worry about the security constraints, because in case of applets, you obviously had worries about the security constraints because you don't know what your application is going to do. Here, you don't need to worry about that stuff. We can define WebAssembly as simple as this. You can run your native code in the browser. That's it. And currently, WebAssembly is supported by these many browsers. And you can run WebAssembly on all those JavaScript engines. So WebAssembly runs on the JavaScript engine, which makes it much more easier. You can write your node application with WebAssembly. And as a whole, WebAssembly is not a language. It's a high-level implementation detail for your language to compile down to WebAssembly, and then you can write stuff on top of it. For example, you have a language. You have to follow the WebAssembly spec, with which you can implement WebAssembly on your language. So it's a spec that is for implementing stuff. So currently, who supports WebAssembly or who has WebAssembly? Obviously, you have C and C++. So you can have libraries that are written in C and C++. You can compile them down using LLVM, and then you can use mscripten, and then compile that down to the bytecodes. And this bytecode, you can go ahead and straightforward use in the browser. Go with 1.11 currently, supports WebAssembly, and it's preliminary now, but it's supported. And you have Kotlin, which also supports WebAssembly, but via Kotlin native. And then finally, we have Rust, which has better support for WebAssembly than compared with all the other things that we have seen. So why Rust? What is Rust? Anybody here used Rust? Okay, we have 2, 3, great. Hear about it? Okay. First time hearing about it. Rest of the people, is it? Okay. So what is Rust? Rust is a system programming language. This is system programming language, which means it's low-level language. It's blazingly fast. The speeds are compared usually with C and C++, which makes it fast, which shows that it is fast. And you don't have dangling pointers. Anybody have worried about dangling pointer in their life before? Okay, there are people. So if you are moved away from C++ just with the fear of dangling pointers and segmentation fault, don't worry, Rust is here to save you. You can just go ahead and do the stuff. And it guarantees thread safety. The language is built for concurrency from the ground up, which makes it more thread safety. So why Rust and WASM together? What makes this combination better? Rust has no runtime, and there is no garbage collection added to it, which means it's smaller binaries. And when you have smaller binaries, you can go ahead and run it anywhere that you want in a much faster fashion. It has better tooling support. We have like a lot of libraries that are added to Rust and Rust environment that can be used to compile down to WebAssembly. And then you can even push those WebAssembly modules into NPM packages. You can package them and push it using WasmPack and tools like that. So we have better tooling for that. It gives you low-level control. Since it's a system-level programming, it can give you low-level control. By control here, low-level control here, I mean like you can drill down to get maximum performance out of your compiler, or else you can just write and that gives you optimal performance. And it also gives you a reliable program. That's one other thing that we have to check. Like in the world of JavaScript, there is a lot of uncertainties there. Like you can write a function that is running faster in Chrome, but that's obviously not running faster in Internet Explorer, because you can have this kind of trade-offs. But here in Rust and WebAssembly, you always tend to have similar performance. They can be like milliseconds of differences, but not much more than that. So we already know this is how JavaScript works, correct? So this is how WASM works. So when the browser sees a WASM module, it goes and downloads the bytecode. It don't need to download the entire bytecode. It's a bytecode and optimized again in prior, which means you can just go ahead and it can do streaming compilation. On fetching first byte, it can decode this entire bytecode and convert that into binary code and then go ahead and compile it. And the compilation here is much more faster than compared to the compilation that happens in the JavaScript cycle. As well as parsing takes much more time than compared with decoding, because decoding is much more faster. Once it is compiled, it's executed, that's it. So no garbage collection process. And streaming compilation, this is something that's really, really awesome, because the moment you get your first byte, your code is ready to run. If the first byte has some information, if you have 10 or 15 bytes that has some information, those 10 or 15 bytes are ready to run, which is awesome. Well, that means it's the end of JavaScript there. Like, you don't need to use JavaScript anymore. No, WebAssembly is not a replacement for JavaScript. It is not introduced to replace JavaScript, but it helps you to surgically insert a WASM module inside your JavaScript application such that you enhance the performance of your overall application. So I see it as the beginning of a beautiful friendship between JavaScript and WebAssembly together. So that's the time for a demo. So let's see what you can do in WASM land. So is it visible for you guys? Everybody is okay? Great. Okay, so I have my WebAssembly application developed here. So basically, it's a JavaScript plus Rust application. That's it. So you have a package.json, actually, and this package.json has all those package dependencies for your JavaScript, and you have this index.html, which has nothing but just some styles. And of course, you have a Webpack configuration file, which does all this Webpack stuff. So it has a Webpack plugin and then WASM plugin. These plugins are responsible for converting Rust into bytecodes, and it's much more easier for us to work in the development environment. And then you have your JavaScript file, which does nothing. It imports the package or the Rust file, and then it runs the function that is called in the Rust world. That's it. And in terms of create, this is where your entire Rust source code lives. And you can see here inside source, I just have one single Rust file. I have a bunch of imports here. That's it. And then I say, this is a run function that I'm going to call from the outside world, from the JavaScript. And then I say, okay, create an element for P, and then set the inner HTML to this content, and then append this entire thing into the document. And here I have a bunch of externals. Like I tried to, okay, so I am calling HTML document, which Rust has no idea about, but I don't want to create the entire HTML document or all the intricacies behind that using Rust. I can just say, okay, this is an external function, you don't need to worry about it. The engine in which you are running, the JavaScript engine knows about this function, you don't need to worry about it. I have a bunch of these things defined. I'll show you another demo in which this can be much more simplified. Great. So that's it. That's basically it. And then I have this cargo terminal file, which has nothing but one dependency, which is compiling down your Rust into stuff. And what I have to do is nothing. It's just the same old workflow. You can go ahead and say npm run start. That's it. So what happens? This entire Rust compilation happens, and the entire Rust compilation happens, and then it converted into WebAssembly module, and then I have a bunch of sets created. So I have my WASM file here. So let's go ahead and see what it has developed. That's it. So it created like this are the things that is running on your native code. I can just go ahead and say. Ouch. That's it. So everything is built in there. Like you don't need to worry about it. It's the same old workflow that you guys have, but you just go ahead and change certain things inside. That's it. And you can add certain things. That's it. So let's go back. It's interesting to see how this happens. Let's see how this happens. A warning ahead for you guys. Only numbers can be passed between WebAssembly and JavaScript. What did I just say? Yes. You can pass only numbers between that too currently. Then how come we saw strings there? Don't you know there are other types exist? Yes, of course, there are other types exist, and people live in those other types rather than numbers. We don't often use numbers. So WASM is here to help. This library is built based on, this library is entirely on Rust. I'm also part of that library, creating it. So it's WASM will help you. So what is WASM as a whole? I consider WASM as a translator that sits between your JavaScript and your WebAssembly. So you have your WebAssembly module, which only knows about the numbers, it's passed inside. And then you have your JavaScript code, which sometimes uses numbers, sometimes uses other objects. And probably there is a translator that sits in between them. That's what WebAssembly, that's what WASM the binding generators. So how WASM does it? Any guesses? Intelligent guesses, guys? Maybe, somewhat related to that. We use array buffers there, typed array buffers, which means like you can get a chunk of memory and then say, okay, this kind of memory, I need to use it. Let's see how it works here. So in your JavaScript file, this is your JavaScript file, you just go ahead and use the binding file that has been generated for you, and then call the function. Consider that you have a function called greet in your Rust code. And this is your Rust function, nothing. You just have a function that takes in a string and it returns the same string. It does nothing for you. And in your JavaScript file, you just say, okay, I'm going to import that particular function from the binding file, not from the WebAssembly module, from the binding file. And here is what my binding file does. Like this binding file is automatically generated. You don't need to worry about this thing. So here it imports everything from the WebAssembly module. And then it exports a function called greet, the same name that you have given in your Rust code. And here it says, okay, it gets an argument, and then it says, okay, pass the string to WASM, which a method is called. And when pass string to WASM is called, the pass string to WASM is nothing but it just gets a string. It encodes a string into array of buffers or array of binaries. And then it just says, okay, allocate this amount of memory for me for doing this stuff, and also set this in the memory, set this values. And then it gives the pointer to that memory and also length of the object that you're going to worry about. That's it. So it gets pointer and the length, as you're seeing here. On the other hand, what happens when the string comes from wasm? It's nothing but it tries to decode this entire thing and get the value from the buffer memory, and then it puts it up. So that's what happens. So you get the pointer and the length, and then it says, okay, it passes this function into the wasm land, and then it returns a value for you. And finally, you're going to free up the memory. The reason why wasm bindgen does this is like, the reason why you should use wasm bindgen when you're developing a Rust and a WebAssembly module is that because it helps you to understand things better, and it clearly helps you to hide those things out of the picture. You don't need to worry about memory allocation, freeing of all those things, because it does automatically for you. Okay, what else can wasm bindgen do for you? You can pass in closures between JavaScript and Rust, because Rust also has a closure, and JavaScript also has a closure. You can pass those things together, to and fro. And you can pass classes to and fro. You can create your JavaScript class entirely in Rust code and then pass those things to the JavaScript layer. Or you can create your entire JavaScript classes and then pass that thing inside the Rust code. Similar to functions, so you can do that same thing for the functions. You can pass in libraries. You're working with node modules. You have a lot of libraries in JavaScript world. You can pass those functions inside Rust. And you can also take those functions outside of the Rust. You can export them out. And there are two other modules that we are developing. One is JSS. This is a crate. The packages in NPM world is called as crate and Rust world. So we have something called JSS, which is helpful for mapping the APIs in the JavaScript world to the Rust world so that you can write your entire application in Rust. And also there is WebSys, which is mapping your web APIs into the Rust world. So let's see the performance. We are talking so much about the performance. Let's check how the performance is. Okay. Don't do this in your production application, guys. Okay. Okay, this is the same application. I haven't changed much. The only thing that was changed is like I added two functions here, Fibonacci series function, and then I'm just calling it multiple times. That's it. It's a Rust code that does Fibonacci, nothing else. And I have a bunch of styles. Let's leave that apart. And it also does nothing. It's just like a plain HTML for you. And then inside my JavaScript, I have this entire thing. The JavaScript also has Fibonacci series, Fibonacci generator, and also it has a list of things. I just add those content to visually see how the performance is. That's it. And then I go ahead and do npm run start. Something happens here. Okay, so what basically it does, like it calculates Fibonacci for a particular number, and then it tries to run it on a loop, both in JavaScript world and also in WASM world. So you can find the differences here. So the 30 factorial is 83.832K. And when it's run on the WASM world, it took less than a second or something. But in terms of JavaScript, it took like more than 12 seconds for you. So that's sort of performance that we are talking about. But yes, this performance is good, but when you're actually developing your JavaScript or WASM application, you mean to have a mechanism in which you have to stop the crossing of boundary between your JavaScript and to the WebAssembly module. There are some serious considerations going on. People are making this thing faster, but when you're doing this jumping quite often, you tend to lose nanoseconds of value, which tends to add up, and you will not get better performance. So you have to structure your application such that it is capable of not crossing that many times between WASM world and here. Right. So the future of JavaScript, future of WebAssembly, you can say. The garbage collection is currently considered to be added into the spec, and they are trying to add a minimal set of garbage collection for the entire WebAssembly stuff, which means any language that is coming out, they can either use this garbage collection that WebAssembly has built in, or they can come with their own garbage collection. These things can change at any point of time. But this is what the current consideration of the community is. Let's see what's going to happen. And how many of you know this thing? JavaScript is single-threaded, right? Of course, it's single-threaded. So what happens in JavaScript? Like, you have a single thread which puts everything into the stack, and then it tries to execute it. There is an event loop concept. And that is a problem in terms of performance. That is also one other problem that you have, because you cannot do things in multiple thread. Doing things in multiple thread is another problem that we have to cater. But here in JavaScript, it's difficult for you. So in WebAssembly, we are also trying to add thread support, which means you can add multiple threads inside the WASM module. WASM module is capable of running in multiple threads. And I think this is one more thing that we have to consider when you're developing your next web application, or when you're changing a web application. Make sure your stakeholders understand that performance is really needed. And those tiny bits of information, those tiny bits of data that you're getting downloaded from the internet will cause performance to go down. And you have to make sure that you're using some stuff to increase the performance of your application. Let me do one more final demo. And this demo is something that we have as an example in our libraries. So I wanted to show that thing. I call myself this one as an advanced demo. But it's a simple demo. And hopefully it works. Yes, the demo works. So this is a plain application that is completely built in Rust. And I can do this. It's a simple paint application that is completely. So the reason why I'm showing this is, like, you can do stuffs with Rust and WebAssembly together. And this is one of the examples. It's just simple application. And if you want to see the code, I can show it. So in JavaScript world, this is what I done. That's it, nothing. I just import this main function. And then in the Rust world, I just say, okay, I'm creating a window. I've said about WebSys, right? So WebSys is the library, which is analogous to your web API. So I just say, okay, I'm going to take the document out of the window object, and then I'm creating a canvas element, which I've done. So once the canvas element is done, I convert that into node, and then I set height and width of the application, of the canvas, and then I make that as an HTML element, because Rust is type language, which means you have to typecast it. There are actually an RFC going on to make sure this as a pleasant experience. It's much more precise, but that will happen. But this is an early API, you can see. And then I get the canvas again, and then I create new cells inside canvas, and then that's it. And here, if you take a look, I'm just adding an event listener there, which is another JSS stuff, like an API in your JavaScript world, and just adding that thing inside here. So this entire function is called dynamically. So whenever I press something there, the call comes to the WASM land, and then it goes back to the JavaScript. So obviously, there is a transition that is happening. Still, you can see I can draw it quite easily, and there is no lag that I can see here. There is no visual lag that you have it here. But of course, whenever I click it, every function, or you know the mouse down, right? So when you press it, it obviously sends events across. So as long as the event is sending, it goes to the WASM. There is a boundary crossing that happens, and then it comes back. That boundary crossing doesn't have any impact in the entire application. And of course, when I release my mouse, the mouse up happens. It also goes out. So things like that happening. So it's an application that is smaller, but it has its own problem. When you're doing in JavaScript, you obviously end up in doing the mouse down, and then the mouse down will take a longer time, and then it goes in a loop, and then you don't know how to control these things. But it really helps here because you know precisely what is happening, and everything is type checked for you. And I guess that's what I have. Any questions you guys have? Yep.
How can you be sure that your compiler doesn't optimize the Fibonacci function to just return a single value?
Sorry, I don't get it. Sorry?
How can you be sure that when you compare performance,
Okay.
it actually went through the function of computing Fibonacci instead of just optimizing out the value from a constant?
You can check it. Like, no, that's okay. You can check it. So this is what you're saying, like when it runs for this many times, how are you confirming that this happens correctly, is it? Yes, because this is something that happens in Rust land, and whenever some function is happening by the Rust code that is emulated, it makes sure it is 100% running the application. So that's why the thread safety and everything happens. It's not like plain forward, it returns something else. But I cannot do a manipulation here, like I cannot add stuffs and then give output there, because it's much more problematic for me. Because it's a huge number, and if I have to do that, then that huge number is not obviously supported. In JavaScript, you have to use big int and things like that, which is not running on multiple browsers. Yeah, I have to trust it. Any other questions? Nope. Yep.
Then, could you elaborate a little more on when these boundaries are actually crossed? Like when you manipulate the DOM or when there are events?
Okay.
What are the events about which you have to be mindful?
Okay, great. That's a good question. I'll just go to this demo and then I'll tell you. So what happens here basically is like this main function is called. That's it. So this main function is called. This main function is related to the main function that is in your Rust code. So this is what is happening as a whole. So once the function is inside here, so you can go ahead, I think you can see it here. So I'm trying to just get the information, like just get the binding file that is generated, which should be much more easier for you to understand. Yep. So the function that goes here, and then you have this set of function, which is called as this set of anonymous function, you can say, which is running on the Rust land. So the main context of this function is like listen to the mouse down event. And the main context of this event is like listen to your mouse move event. So whenever a mouse down is happening, then what it does is like it converts this entire thing, and then it takes the value from the JavaScript, from your browser to the JavaScript, and from the JavaScript, it passes this thing to the WebAssembly module that is created. So your WebAssembly module obviously listening there, so there is a boundary crossing there. And once it listens, it has to send some feedback back to the Windows or the browser, which means this has to take the same path again. So it crosses the boundary, comes to the JavaScript land, and first it interacts to the binding file that is generated, and then goes to the JavaScript file, and then back to the browser. So that's how this thing happening. So whenever you do a mouse down once, it goes to the WebAssembly, there is a boundary crossing once, and then it gives feedback, there is a second boundary crossing that's happening. And you have to be mindful about this boundary crossing. Because, for example, the Fibonacci function that I've shown, the entire 1 million or 1,000 or times that it is running, it's running entirely on the Rust side. That makes it much more faster. But if you're trying to run this 1 million loop and then putting that loop in the JavaScript side and then calling the WebAssembly module inside the JavaScript file, which means you're crossing the boundary for 1 million times. And in that case, it's much more cost effective. I mean, you cannot see the obvious performance improvement with the WebAssembly, and that's the boundary crossing is not something that has to be crossed multiple times. That's the crux of it. Yes.
It means that when you manipulate the DOM a lot, you have this boundary crossing, right?
Yes, you will have a boundary crossing, and that's why I think WebAssembly also don't support DOM straight away, and that's why we have built something like WebSys and JSys in order to help or enhance that functionality. But yes, when you're manipulating with DOM, I think JavaScript is your go-to stuff. But when you have certain parts of that application where the performance is so intensive that you need to calculate, then you can go to WebAssembly land and then come back here.
So the best effect is obtained when you use it for computations, basically.
Yes.
Okay. Thank you.
Yes.
So at the beginning, you say that you can start executing as soon as you get your first byte.
Mm-hmm.
But I guess, so if the byte is a jump,
Okay.
it will just wait, right? Until it gets that address.
Yes, of course. You need to have something meaningful before this entire thing is getting executed. Yeah. But the concept of streaming compilation is like, which is of course coming to JavaScript, which we've people are working on it, community is working on it. But now, what you can with WebAssembly module is like you have hundreds of functions defined in your module, and then there is just one function that is coming in, and you're calling that function from your browser. Then that function is executed for you, which means that will never happen in JavaScript world because it has to wait till the entire thing is downloaded, and you have to wait till the entire stuff's running.
But it actually starts executing until it gets to a point where
it starts executing as soon as it has its first byte. So for the very first byte of the WASM header will be like, it says like, this is MIME type of WASM. The moment it receives that, it can compile that down and then put it in the engine saying that WASM module is coming down and you have this thing. Everything is set for you. So the next byte comes down, it converts that byte into compiles that byte and then puts again to that engine. And then the streaming compilation happens like every nanosecond, something like that. And then it does all those things for you.
Just saying, if you need to call a function, if the first byte is a function call, you need to have that function already compiled.
Yes.
At that given address.
Yes. First function is a function call, then it has to be compiled, but you need to have those bytes. If you have those bytes, then it does the work for you.
So you also said that you wanted to add a primitive for concurrency. So it would be a good idea to do a parallel request to external systems in Rust, for example, instead of JavaScript, because you cannot do
all those external communication, of course, happens via the browser. That's why the sandboxing thing come into picture. If you're doing that stuff, then you're obviously losing the security, so that is not possible. And also the entire threads in terms of WebAssembly world is something that relies on the OS, and it takes the thread from the OS and then operating system, and then it runs on top of it. But it's not completely done. We have some experiments that are working with threads, but it's not completely done yet. Thank you.
Yeah, you said that for crossing boundaries, you're using that library which parses the input and gives it back between the two languages. Is that only for Rust, or is it also for...
Yep, currently this is only for Rust, and we just started experimenting this stuff with C++. But of course it is doable, but we need to do certain hacks to the code in order to make sure that it works perfectly. But yes, currently this is exclusively developed for Rust, but it will be moved towards other libraries such that we are envisioning that all the other programming language which wants to compile down to Rust, or which wants to compile down to WebAssembly module, you can use this library in order to make this thing done.
Okay,
but
and
not now.
That's because every language has different data structures, and
yes,
so
exactly.
you have to adapt them. Okay.
We need to add in the parsers for this language, and that is a huge job that we have to do.
Okay, thank you.
Thanks. Okay, guys. Thank you very much. Thanks for your time.